Hello, my name is Christian Bishop, and this is Lab 4, magnets. In this presentation, I'll go over the purpose of the lab, our initial setup, the data we collected, my code, and finally the results, and some what-if analysis at the end. So the purpose of this lab was to measure the distance-dependent magnetic field of a small bar magnet. We based our experiment on three main laws: the Biot-Savart law, which relates magnetic field to a current element; the magnetic field of a dipole, which is similar to an electric dipole but has closed circulation; and the distance dependence formula, which shows that the magnitude of a bar magnet's field decreases with distance. Biot-Savart's on the top right, and then the bottom two are at the bottom. Quick preview of our results. N was equal to negative 2.2943, and our magnetic dipole moment came out to be 5.98. Here are initial variables. So our model was a natural log of Bx versus the natural log of R, which shows how magnetic field changes logarithmically with distance. We assumed that there was no other magnetic field affecting the magnometer besides our magnet and the Earth's magnetic field. Our system was the magnometer itself and the surroundings of the bar magnet, the Earth, and any nearby objects that may slightly interfere, even though we assume that those you know, aren't doing that. Last, our condition was setting the magnometer's exponent to 0 before starting measurements. To set up the experiment, we first compensated for true magnetic north. We laid the phone flat on the table with the magnometer app open and rotated until X reading was exactly 0. Then we aligned the meter stick with the axis and placed the bar magnet at one end of the stick. Then we slid the phone on a perpendicular line to the meter stick. This made sure that the Z component of the field stayed relatively constant. We marked tape when the Y component was minimal and then when the X component was minimal, and the intersection of these two tapes marks where the phone's magnometer is. That gave us the point of reference for like taking all of our distance readings at the front of the experiment. Here's our data sheet. The graph shows the natural log of Bx versus the natural log of R, and from that we get a fairly linear relationship confirming the inverse squared type dependence. We expected for the magnetic fields from that formula earlier. Um, you see the data points trending closely to a line, but there's a bit of a scatter. I could do some small measurement errors. This is our coding. So we modeled the magnetic field using the Biot-Savart law, the dipole formula. We calculated the magnetic dipole moment as 5.98. From there, determine the magnitude of the field using the components of distance, Rx, Ry, and Rz. The code computed the r hat vector and then used it to find the magnetic field vector at different points along the x-axis. We visualize the results using arrows for the direction and the magnitude of the magnetic field. Each has 6 sample points: positive and negative x, y, and z. For our results, data mostly match the theoretical model, but not perfectly. There were similarities overall, but also small consistencies likely caused by not aligning the magnometer perfectly with north. There's slight measurement errors in placing the tape, or even small environmental magnetic interference from like nearby phones or other like electromagnetic devices. These all could contribute small shifts to the readings. What if? What does it mean? Uh, First, what if we hadn't oriented the experiment to compensate for the true north? Then the Earth's magnetic field would have interfered significantly with our readings. It created like a bunch of errors and deviations from the expected results. Second, what if we had stuck two identical magnets together end to end and run the same experiment? Pretty much everything would be the same, other than the magnitude of everything would change by a factor of 2. So all the measurements would be twice as far away or twice as close or whatever. So overall, this lab confirmed that the magnetic field of the bar magnet decreases with distance, and our results align with theory within a reasonable margin of error. Solid demonstration of Biot-Savart law and dipole field moment in practice. Thank you for listening.